Hi, welcome all to the online classes for engineering physics, BTech Agriculture first semester. Topic atomic theory. Now, as we all know, all about the atomic theory. So, atomic theory, all matter is made up of atoms, atomic parts, protons, positive, some mass in nucleus, neutrons, no charge, some mass in nucleus, electrons, negative charge, no real mass, but do take up most of the space around an atom. This is the atomic structure, the microscopic view of the atomic structure. Nucleus, orbits, electrons, protons. Describing atoms. A atomic number. Atom is describing by atomic number and atomic mass. Atomic number equals to number of protons in a neutral atom, zero charge. That is, the protons is equals to the electrons. Atomic mass equals to number of neutrons plus protons. Changing parts, the number of protons for an atom never changes, but the number of neutrons can change. Isotopes are atoms of same element with different number of neutrons. Yes, isotopes, same atomic number but different mass number. Same and different atomic number but same mass number. Isotopes. Isotopes are the atoms having the same atomic number but the different mass numbers. Example of isotopes: hydrogen, atomic number 1; tritium, atomic number 1. But the masses are different. The atomic mass in hydrogen is 1 and the atomic mass in tritium is 3. Deuterium, atomic number 1, the mass number is 2. Isotopes of hydrogen, all atoms have an atomic number of 1. They all have one proton. The mass numbers are different because the number of neutrons are different. As you see in the slide, ions. An atom that gains or loses an electron is called ion. If the atom loses electron, it becomes positively charged. That means it is having a deficiency or it becomes a positively charged. If an atom gains electrons, it becomes negatively charged. What? Remember, proton is equals to electron. So if we change those numbers, the charge moves in the direction of the larger number of particles. More on this later when we talk about bonding. Ion examples: a sodium atom when add with chlorine atom. Finally, a sodium will become a positive and chlorine will become a negative, and they just share a bond because as the sodium is having one extra valence electron and chlorine is having a one valence electron, so they want to make a covalent bonding and the salt is produced. Atomic theory, early theory, given by Aristotle, second given by Democritus. Aristotle was more popular than Democritus, so this theory was ignored for over 2000 years. Modern theory, given by Dalton in England in about 1800, Dalton atoms, Dalton atomic theory. All elements are composed of atoms and they are indestructible like solid sphere. They cannot be created or destroyed. Law of conservation of matter given by Dalton. Atoms of the same element are exactly alike. Atoms of different elements are different. Compounds are formed by the joining of atoms two or more elements. Second modern theory is given by Thomson in 1897, England, discovered negatively charged electrons. And the third modern theory is given by the Rutherford in 1897, England. uh, In England, in 1908, discovered the nucleus. Bohr in 1913 used the atomic structure. Denmark said electrons were in orbits of energy levels around the nucleus. Energy levels. Bohr gives the atomic structure. He gives that the protons and neutrons are concentrated on the center and known as nucleus, where the electrons moves around the nucleus in the orbits of different energy levels, E1, E2, E3, E4. The energy that an electron is based on its location around the nucleus. Electrons that are closer to the nucleus have less energy than those that are further away from the nucleus. Energy levels, first to second electrons. Energy first, level first is having two electrons. This is the electronic configuration of energy level. First, two electrons. Second, eight electrons. Three, eight electrons. Fourth level having 18 electrons. Five level having 32 electrons. Each level must be full before another can be started. Example: a nickel has an atomic number of 28. Level 1 hold 2, 26 to place. Level 2 can hold 8, 18 to place. Level 3 can hold 8, 10 to place. Level 4 can hold 18. But only 10 are left, so it will only have 10 in it. We have to show neutrons and protons too. Protons, electrons are usually equal, so we know there are 28 protons. Neutrons are found by subtracting the atomic number from the atomic mass. So atomic mass 59, atomic number 28 is equals to 31 neutrons. It would look like this. See the animated view of electrons. Okay. So after visiting some of the applications of different aspects of atomic physics, we now return to the basic theory that was built upon the Bohr's atom. Einstein's once it was important to keep asking the question we eventually teach children not to ask. Why is angular momentum quantized? We already know the answer. Electrons have wave-like property. As de Broglie later proposed, they can exist only where they interfere constructively and only certain orbits meet proper conditions. As we shall see in the next module, Bohr's initial work on hydrogen atom a decade was to pass before de Broglie proposed that matter has wave properties. The wave-like properties of the matter were subsequently confirmed by observations of electron interference. When scattered from crystal, electrons can exist only in locations where they interfere constructively. How does this affect electrons in atomic orbits? When an atom is bound to an atom, when an electron is bound to an atom, its wavelength must fit into a small space. something like standing wave on string. Allowed allowed orbits are those orbits in which an electron consequently interfere with itself. Not all orbits produce constructive interference. Thus, only certain orbits are allowed. The orbits are quantized. For circular orbit, constructive interference occurs when the electron's wavelength fits nearly into the circumference, so that wave creates always align with crest and wave tough align with tough, as we will see in the figure. More precisely, when an integral multiple of electrons uh, wavelength equal the circumference of the orbit, constructive interference is obtained in equation form. The condition for constructive interference and allowed electrons orbit is n lambda. So we will see later on. Electron cloud model. Electrons travel in regions called electron clouds. You cannot predict exactly where an electron will found. Electron moves in. This is the atomic Rutherford atomic model or atomic structure model or Bohr's model. Bohr's atomic structure model. Electrons are moving like anything in the orbits, and protons and neutrons combinedly form a nucleus and located in the center. Now, Democritus 460 BC, a Greek philosopher, suggested the world was made of two things: empty space and atomos. Atomos, Greek word for untouchable. Two main ideas: atoms are the smallest possible particle of matter. There are different types of atoms for each material. John Dalton's atomic theory, 1804, all matter is made up of atoms. Atoms of one element are all the same. Atoms cannot be broken down into smaller parts. Compounds formed by combining atoms. Dalton's early atomic model, billiard ball model, he envisioned atoms as solid, hard sphere like billiard balls, so he used wooden balls to model them. J. Thomson in 1897 discovered the electron. He was the first scientist to show the atom was made of even smaller things. This is the cathode ray tube to discover electrons given by J. Thomson. Thomson experiment. A voltage source is applied across the cathode ray tube. A vacuum is filled between the two metal discs. Passing an electric current makes beam appear to move from the negative to positive end. Slowly and slowly, the electric current makes a beam appear to move from negative to positive end. By adding an electric field, by adding an electric field vertically or horizontally, the beam will divert somehow like this. If you see, adding an electric field caused the beam to move toward the positive plate. Thomson concluded the beam was made up of negative moving pieces. Negative moving pieces. So Thomson plum pudding atom model, a spherical cloud of positive charge, electron, Democritus Dalton Thomson video. Eugen Goldstein, 1850-1930, using a cathode ray tube, he discovered canal rays, which are beams of positive charge particles. Of positive charge particle. He is credited with the discovery of protons in an atom, canal discovery. So, we say that atomic theory is a scientific theory that matter is composed of particles called atoms. Atomic theory traces its origin to an ancient philosophical tradition known as atomism. According to this idea, if one were to take a lump of matter and cut it into even smaller pieces, one would eventually reach a point where the pieces could not be further cut into anything smaller. An ancient Greek philosopher called these hypothetical ultimate particles of matter atmos, a word which means uncut. I had already discussed. In the early 1800s, the scientist John Dalton noticed that chemical substances seem to combine and break down to other substances by weight in proportions suggested that suggested that each chemical element is ultimately made up of tiny invisible particles of consistent weight. Shortly after 1850, certain physicists developed the kinetic theory of gases and of heat, which mathematically model the behavior of gases by assuming that they were made up of particles. In the early 20th century, Albert Einstein and Jean Perrin proved the Brownian motion, the erratic motion of the falling grains in water, is caused by the action of water molecules. The third line of evidence silenced remaining doubts among scientists as to whether atoms and molecules were real. Throughout the 19th century, some scientists had cautioned that evidence for atoms was indirect, and therefore atoms might not actually be real, but only seem to be real. By the early 20th century, scientists had developed fairly detailed and precise models for the structure of matter, which lead to more rigorously defined classification for the tiny invisible particles that make up ordinary matter. An atom is now defined as the basic particle that comprises or composes a chemical element. Around the turn of the 20th century, physicists discovered that the particles that chemists called atoms are in fact agglomerations of even smaller particles, subatomic particles, but scientists kept the name out of convention. The term elementary particle is now used to refer the particles that are actually invisible. Now, if I'm just talking about the history or philosophical atomism, the idea that matter is made up of a discrete unit is a very old idea. Appearing in many ancient cultures such as Greece and India, the word atom, meaning uncuttable, was coined by Greek philosopher Leucippus and his pupil Democritus. Democritus thought that atoms were infinite in number, uncreated, and eternal, and that the qualities of an object result from the kind of atoms that compose it. Democritus' atomism was refined and elaborated by the Greek philosopher Epicurus around 341 270 BC and by the Roman Epicurean poet Lucretius. During the early Middle Ages, atomism was mostly forgotten in Western Europe. During the 12th century, it became known as, again, Western Europe through reference to it in the newly discovered writings of Aristotle, the French Catholic priest Pierre Gassendi reviewed Epicurean atomism with modification, arguing that atoms were created by God, and though extremely numerous and not infinite, he was the first person who used the term molecule to describe aggregation of atoms. Near the end of 18th century, two laws about chemical reactions emerged without referring to the notion of an atomic theory. The first was the law of conservation of mass, closely associated with the work of Anthony Lavoisier, which stated that the total mass in a chemical reaction remain constant. The second was the law of definite proportion, first established by the French chemist Joseph Proust in 1979. This law states that if a compound is broken down into its constituent chemical elements, then the masses of the constituents will always have the same proportion by weight, regardless of quantitative source of the original substance. Now, John Dalton studied and expanded upon this previous work and defended a new idea, later known as the law of multiple proportions. If the same two elements can be combined to form a number of different compounds, then the ratio of the masses of two elements in various compounds will be represented by small whole number. This common pattern in chemical reaction that was observed by Dalton and other chemists at that time. Uh, Dalton used the term atom to refer to the basic particle of any chemical substance, not strictly for elements, as is the practice today. Dalton did not use the word molecule; instead, he used the terms compound atom and elementary atom. Dalton proposed that each chemical element is composed of atoms of a single unique type, and though they cannot be altered or destroyed by chemical means, they can combine to form more complex structure. This marked the first truly scientific theory of the atom. Then Dalton reached his conclusion by experimentation and examination of the results in an empirical fashion. In 1803, Dalton referred to a list of relative atomic weights for a number of substances in a talk before the Manchester Literary and Philosophical Society on the solubility of various gases such as carbon dioxide and nitrogen in water. Dalton did not indicate how he obtained the relative weight, but initially hypothesized the variation in solubility uh, was due to difference in masses and complexity of the gas particles, an idea that he abandoned by the time the paper was finally published in 1805. Over the years, several historians have attributed the development of Dalton atomic theory, but to his study of gaseous solubility. But a recent study on his laboratory notebook entries concludes he developed the chemical atomic theory in 1803 to reconcile Cavendish and Lavoisier's analytical data on the composition of nitric acid, not to explain the solubility of gases in water. After that, Thomas Thomson published the first brief account of Dalton's atomic theory. Now, Milken's oil drop experiment determined the charge on an electron. Use Thomson charge to mass ratio to calculate the mass of electron. Milken's oil drop experiment. Milken's oil drop experiment. Another video. These are the some video links. You just refer. Ernest Rutherford in 1913 discovered the nucleus of gold atom with his gold foil experiment. So this is the Ernest Rutherford gold foil experiment. You see in the figure. A alpha particle emitter emits alpha particle on a gold foil. There's a detecting screen is there. Rutherford gold foil experiment. Radioactive sources, alpha rays strike on the gold foil in the detector location. Using J.J. Thomson plum pudding atomic model, Rutherford predicted the alpha particle would pass straight through the gold foil. That's not what happened. That's not what happened. Plum pudding atomic model. Electrons scattered throughout, and the path of particle pass on through the gold foil. So that was happened at the time. Most alpha particles go straight through the gold foil. A few alpha particles are sharply deflected. So this is the actual result. The atom is mostly empty space. There is a small dense center with positive charge. Rutherford discovered the nucleus in atoms. This is the Rutherford atomic model. Rutherford's contribution to the atomic theory. The atom is mostly empty space. The nucleus is small, dense core with a positive charge. Gold foil video or Rutherford's atomic model. Structure of the atom. Atom, the smallest particle of an element that can exist alone. Two regions of an atom: nucleus, center of the atom, protons and neutrons, electron cloud, area surrounding nucleus, containing electrons. The structure of the atom: proton plus neutron, electron. Proton positive charge, one atomic mass unit found in the nucleus. AMU approximate mass of proton or neutron. Neutron neutral charge, one AMU found in the nucleus. Electron negative charge, mass is very small. Now, if I'm talking about carbon, atomic number 6, hydrogen, helium, lithium, beryllium, boron, carbon. Atomic number 6 and atomic mass is 12.011. Boron having atomic number 5, atomic mass 10.81, and the symbol is B. Atomic number protons in nucleus. The number proton determine identity of the element. Mass number, atomic mass, number of protons plus neutrons. Units are gram per mole. Counting atoms, isotopes, atoms of same element with varying atomic number. Atoms of same atomic and number but different mass number. You can see the same element with varying number of neutrons. Different isotopes have different mass number because the number of neutrons is different. Composition, counting atoms. This is a presentation or representation of an atom or element where superscript A refer to mass number of protons, number of neutrons, plus subscript Z refers to atomic number, number of protons or electrons. So example of helium, element symbol, nuclear symbol notation. Protons have positive charge and electrons have negative charge. In a neutral atom, the number of protons equals the number of electrons, so the overall charge is 0. Helium is an atom number 2, has 2 protons and 2 electrons when stable. In a neutral atom, atom number equals number of protons of electrons. Sometimes atom will gain or lose electrons and form ions because an electron has negative charge. When an atom gains electrons, it becomes negative. When the atom loses electrons, it becomes positive. Cation, a positive ion, anion, a negative ion. Let's do some practice for some atomic elements or elements. Aluminum, proton 13, neutron 14, atomic mass number. We need to fill this. Let's practice nuclear symbol notation. Nuclear symbol notation, proton, electrons, neutrons, atomic number. So just fill these criteria by analyzing the element. Uranium 235, potassium, atomic number 19, mass number 39.098. Now there are some questions or quiz time. How hydrogen atom is different from atoms of all other elements? What is discharge tube? Name the subatomic particle present in an atom. What is an electron? What is its relative mass and charge? What is the relative mass and charge of an electron? Yes. What is the relative mass of charge of an electron? Some MCQ. Before moving to these questions, I would like to give one more note that Thomson plum pudding model was disapproved in 1909 by one of his former students, Ernest Rutherford, who discovered that most of the mass and positive charge of an atom is concentrated in a very small fraction of its volume, which he assumed to be the very center. Ernest Rutherford and his colleague Hans Geiger and Ernest Marson came to have doubts about the Thomson model after they encountered difficulties when they tried to build an instrument to measure the charge to mass ratio of alpha particles. These are positively charged particles emitted by certain radioactive substances such as radium. The alpha particles were being scattered by the air in the detection chamber, which made measurement unreliable. Thomson had encountered a similar problem in his work on cathode rays, which he solved by creating a near perfect vacuum in his instruments. Rutherford did not think he had run into this same problem because alpha particles are much heavier than electrons. According to Thomson model of the atom, the positive charge in atom is not concentrated enough to produce an electric field strong enough to deflect an alpha particle. And electrons are so lightweight they should be pushed aside effortlessly by the much heavier alpha particle. Yet there was scattering, so Rutherford and his colleagues decided to investigate this scattering carefully. Between 1908 and 1913, Rutherford and his colleagues performed a series of experiments in which they bombarded tinfoils of metal with alpha particles. They spotted alpha particles being deflected by angles greater than 90 degrees. To explain this, Rutherford proposed that positive charge of the atom is not distributed throughout the atom's volume as Thomson believed, but is concentrated in tiny nucleus at the center. Only such an intense concentration of charge could produce an electric field strong enough to deflect alpha particles as observed. First steps towards a quantum physical model of the atom. The planetary model of the atom had two significant shortcomings. The first is that, unlike planets orbiting a sun, electrons are charged particles. An accelerating electric charge is known as emit electromagnetic wave according to Larmor formula in classical electromagnetism. An orbiting charge should steadily lose energy and spiral towards the nucleus, colliding with it in a small fraction of a second. The second problem was that planetary model could not explain the highly peaked emission and absorption spectra of atoms that were observed. Quantum theory revolutionized physics at the beginning of the 20th century when Max Planck and Albert Einstein postulated that light energy is emitted or absorbed in discrete amount is known as quanta. In 1913, Niels Bohr incorporated this idea into his Bohr model of the atom, in which an electron could only orbit the nucleus in particular circular orbits with fixed angular momentum and energy. Its distance from the nucleus being proportional to its energy. Under this model, an electron could not spiral into the nucleus because it could not lose energy in continuous manner. Instead, it could only make it instantaneous quantum leaps between the fixed energy levels. When this occurred, light was emitted or absorbed at frequency proportional to charge in energy. Bohr model was not perfect. It could only predict the spectral lines of hydrogen. It could not predict those of multi-electron atoms. Worse still, as spectrographic technology improved, additional spectral lines in hydrogen were observed which Bohr's model could not explain. In 1960, Arnold Sommerfeld added elliptical orbits to the Bohr model to explain the extra emission lines, but this made the model very difficult to use and it still could not explain more complex atoms. Now, discovery of isotopes is just while experimenting with the products of radioactive decay. In 1913, radiochemist Patrick Soddy discovered that there appeared to be more than one element each position on the periodic table. The term isotope was coined by Margaret Todd as suitable name for these elements. That same year, J. Thomson conducted an experiment in which he channeled a stream of neon ions through magnetic and electric field, striking a photographic plate at the other end. He observed two glowing patches on the plate, which suggested two different deflection trajectories. Thomson concluded this was because some of the neon ions had a different mass. The nature of this differing mass would be later be explained by discovery of neutrons. And now the discovery of nuclear particles. In 1970, Rutherford bombarded nitrogen gas with alpha particles and observed hydrogen nuclei being emitted from the gas. Rutherford concluded that hydrogen nuclei emerged from nuclei of the nitrogen atoms themselves. That is, in effect, he had a split in nitrogen. From his own work and the work of his students Bohr and Henry Moseley, Rutherford knew that the positive charge of an Na atom could always be equated to that of integer number of hydrogen nuclei. This, coupled with the atomic mass of many elements being roughly equivalent to an integer number of hydrogen atoms, then assumed to be the lightest particle, led him to conclude that hydrogen nuclei were singular particles and a basic constituent of all atomic nuclei. He named such particles protons. Further experimentation by Rutherford found that the nuclear mass of the most atoms exceeded that of the protons it possessed. He speculated that this surplus mass was composed of previously unknown neutrally charged particles which were tentatively doubled neutrons. In 1928, Walter Bothe observed that beryllium emitted a highly penetrating electrical neutral radiation when bombarded with alpha particles. It was later discovered that this radiation could knock hydrogen atoms out of paraffin wax. Initially, it was thought to be high energy gamma radiation, since gamma radiation had a similar effect on electrons in metal, but James Chadwick found that ionization effect was too strong for it to be due to electromagnetic radiation so long as energy and momentum were conserved in the interaction. In 1932, Chadwick exposed various elements such as hydrogen and nitrogen to the mysterious beryllium radiation, and by measuring the energies of the recalling charged particles, he deduced that the radiation was actually composed of electrically neutral particles which could not be massless like the gamma ray, but instead were required to have a mass similar to that of proton. Chadwick now claimed these particles as Rutherford neutrons. For his discovery of neutrons, Chadwick received the Nobel Prize in 1935. So there is many more and lot of data according to the history point of view. Now come to the some questions, MCQ questions. In 1903, who had proposed the model of an atom, due to which electrons and protons were known to us? Obviously, J.J. Thomson. Which model of an atom is similar to Christmas pudding? Rutherford, Thomson, Dalton. We had studied that and we had discussed that Thomson pudding model. So, Christmas pudding. Uh, exactly resemble to the model of an atom. The present concept of the structure of an atom is given by which scientist? The present concept of structure of an atom is given by which scientist? Niels Bohr. Next, name an electron in which the nucleus of the atom does not contain any neutrons. Hydrogen. Which model does not able to explain the stability of an atom? Rutherford's model. According to Goldstein experiment on passing high voltage electricity through gases at very low pressure resulted in the discovery of proton. Who had discovered electron? Obviously, according to the theory of which we had seen or studied, it was Niels Bohr. In 1932, who had discovered neutron? Uh, we had just completed the topic in the very last that James Chadwick in 1932 who had discovered the neutron. Which model describes that there is no change in the energy of electrons as long as they kept revolving in same energy level and atoms remain stable? Bohr's model. And the last question, next. The correct electronic configuration of sodium is 281, 821, 218, 282. Yes, the atomic number of sodium is 11, and according to the configuration we had seen in the previous slides, this come out to be 281. The option A is the right answer. So this is all about the brief history or the introductory of the atomic structure, atomic model, or atomic atom, or its classification according to the various scientists. Now, in the next lecture, we are going to discuss with the uh, wave nature and particle nature of atom. So, thank you all. One second. Thank you.